Of the Earth's surface are crumpled, torn apart, and patched together again. Over countless millennia, this restless activity has forced mountains skyward, ripped huge faults hundreds of miles in length, and formed whole continents that in turn have been further carved and etched by water. This process of change has shaped and reshaped the landscape, sometimes taking eons, sometimes only moments.
Vancouver! Vancouver! This is it!
Today, the changes caused by the eruption that day in 1980 are clearly recorded in the landscape of Mount St. Helens. The eruption was, in fact, a series of events. Each had its distinct impact on the landscape, an impact that we can read in the evidence that remains. From here at Johnston Ridge Observatory, we can see where the eruption began, on the north side of the mountain. Suddenly, the flank collapsed, creating the largest landslide in recorded history. The entire top of the mountain rushed downslope towards Johnston Ridge at 150 miles an hour, burying the forest. As the landslide split the mountain open, it unleashed the tremendous pressure that had been building within. The blast was a great sideways explosion of rock fragments, ash, and hot gas, and it roared across the landscape at speeds greater than 300 miles an hour. The blast raced ahead of the landslide in the valley below the mountain, hit the surrounding old-growth forest with its super-hot stone-filled wind, and created 3 distinct zones. Close to the volcano, including Johnston Ridge, trees caught in the full intensity of the blast were ripped from the ground, shattered, and became part of the blast. Farther away, where the blast was less intense, trees up to 8 feet in diameter were toppled, their trunks pointing in the direction of the blast. Still farther away, as the blast weakened, its heat was still fierce enough to sear the trees and leave a standing, dead forest. Meanwhile, the landslide continued to rumble on, bringing more change to the already blast-affected landscape. At Spirit Lake, where the blast had knocked down trees on the surrounding hillsides, the landslide barreled in. It bounced off Harry's Ridge, plowed through the lake, and deposited great chunks of the mountain, called hummocks, in the lake's far cove. As the landslide hit the lake, it shoved huge waves 800 feet up the surrounding hillsides. When the water rushed back down, it carried the trees blown down by the blast and dumped them into the lake. On the other side of Harry's Ridge, the landslide stripped off the vegetation, exposing bare rock. Nearby, at Johnston Ridge, the landslide surged up and over, spilling hummocks across the crest. But the bulk of the landslide was diverted westward by Johnston Ridge and slid into the North Fork Toutle River Valley. The river was completely buried under a layer of rock and debris 600 feet deep in places. Hummocks were strewn through the river valley. The landslide dammed tributary streams that later would form whole new lakes. And low-lying areas of this new landscape filled with water to form ponds and wetlands. Then, with the blast exhausted and the landslide rumbling to its end, another part of the eruption gained strength. On the flanks of the mountain, the fierce heat released by the blast swiftly melted snow and glacial ice, creating heavy slurries of mud, boulders, and tree trunks. But the most powerful mud flow poured out of the landslide through the valley of the North Fork Toutle River and flowed downstream for hours, snatching homes and bridges on its way. And there was still more to come. The eruption reached its climax in the afternoon, when molten rock poured out of the crater, gushing forth great quantities of super-hot pumice, gas, and ash, called pyroclastic flows. They buried the hummocks below Johnston Ridge, forming a smooth plain. As these pyroclastic flows proceeded, they boiled the groundwater beneath the surface, creating trapped pockets of steam that exploded like renegade geysers, and blasting craters up to a quarter-mile across. Throughout the day, the mountain pumped hundreds of millions of tons of ash into the atmosphere, creating a column above the crater that roiled 12 miles high. Winds carried the ash eastward, turning day into night, blanketing the landscape, and eventually encircling the planet. Within days, Geological Survey scientists returned to the now barren, steaming landscape to re-establish their monitoring efforts.
We considered the volcano to still be extremely dangerous. We felt it was going to erupt again, but we didn't know when. So our job was to predict future eruptions if we could and give warning.
Within months, molten rock erupted onto the crater floor, cooled and hardened, forming a lava dome. Over time, the dome grew as more eruptions added layer upon thick layer of lava. Scientists focused their monitoring on this lava dome.
We saw several different patterns of activity before these dome eruptions, and we learned to recognize these patterns as warning signs that an eruption would soon occur.
Ground cracks would often appear and widen on the dome. The dome would steadily swell from as little as an inch a day to as much as 5 feet in an hour.
156.123. Well, that's a big change from last time, isn't it? 15 centimeters, 6 inches or so?
The number of earthquakes taking place beneath the dome would increase until there were hundreds each day.
We've got a pretty good event happening now. Boy, I'd say it's a good idea to get people out of there.
Then, within a matter of hours, an eruption would happen. This hot new lava oozed onto the dome. Massive chunks of it would crash down the side of the dome to the crater floor.
By studying the pattern of these warning signals, scientists were able to predict most of the mountain's later eruptions as much as 3 weeks in advance.
Mount St. Helens gave us a wonderful testing ground. Because there were so many eruptions, we could devise and test new strategies for predicting volcanic activity.
The knowledge gained at Mount St. Helens is now regularly applied by scientists to predict the eruptions of other volcanoes around the world.
But not all volcanoes erupt in the same way. Some, like Mount St. Helens, erupt lava explosively or in thick flows. Others, like Hawaiian volcanoes, tend to erupt fluid lava non-explosively.
So not only do we try to predict when an eruption will take place, but also what kind it will be, how explosive, and therefore how dangerous.
Although different, all types of volcanoes play a profound role in building the surface of the Earth. The floors of our oceans, the ground beneath our feet. For all the dramatic change that the Mount St. Helens eruption brought to the landscape, it was a relatively small expression of the Earth's dynamic nature. Just one event in the life of one of our world's several thousand volcanoes, over 50 of which are active during any given year. Mount St. Helens itself has experienced hundreds of eruptions, some of them much larger than the 1980 event. But because we were eyewitnesses to that eruption, its message was delivered with exceptional impact. And we still can read it in the mountain today. The Earth is a living planet. And the landscape we walk today is not what it was yesterday, nor what it will be tomorrow.
enjoyed our theater presentation today. Please exit through the open doors at the front of the theater.